Hello and welcome to this third film in the series of films about higher level bonding. This one deals with the first of the intermolecular forces that we introduced in the previous film. They are the dispersion forces, and it would definitely be useful if you have some idea about what intermolecular forces are and about polarity of molecules before you start watching this one. So if you haven't watched the first two films in the series, I'd advise you to do so before watching this one. Anyway, hopefully by the end of this film what you'll be able to do is explain why dispersion forces arise in molecules, and also why one molecule might have stronger or weaker dispersion forces than another. Now you might remember when we were looking at atomic structure, talking about the fact that electrons, there's a probability of finding electrons in certain regions of space, and we call these regions of space orbitals, and a collection of orbitals leads to an electron cloud around an atom. Now if an atom has an electron cloud, then any molecule that's made of atoms will also have an electron cloud. But let's just stick to the example of an atom, just because these two diagrams involve atoms and not molecules. We could imagine this electron cloud being symmetrically distributed around the atom or unsymmetrically distributed. And in fact, there's this constant flux between one state and the other because the electrons can move, or rather the shape of the electron cloud can change from one moment to the next. This happens on an extremely short time scale. I mean, we're talking about 10 to the minus 15 seconds, and these are times that we've only recently even begun to be able to measure. I mean, we've been able to imagine them for some time, but only now are we becoming able to measure these time scales. And if this electron cloud did happen to wobble over here, and there was a greater amount of electron density over this side of the atom or molecule, but we're talking about atoms here, then this side would become slightly negative because there'd be an uneven distribution of charge, which, as we know, we call a dipole. Because this dipole is just happening for a fleeting moment in time, it's called an instantaneous dipole. So here we've got a helium atom with its electrons down here. It's going to have an instantaneous dipole where it's slightly negative down here and slightly positive down there. If there happens to be another atom of helium nearby, then its electron cloud will feel this uneven distribution of charge and will be attracted towards the positive end. So there'll be a dipole in this helium atom as well, but this will be induced rather than just happening instantaneously. Induced as in it's been caused by the neighbouring atom. Once these two atoms both have a dipole, there will be an attraction between their positive and negative ends. So as a result of this instantaneous and induced dipole, there's an attractive force. As I've said, this movement of electrons is random and it's taking place over an extremely short space of time. So we shouldn't expect this attraction to last very long or for it to be very strong. Okay? As with all these forces that we're looking at, we need to decide what kinds of molecules will have them and what kinds of molecules will have the strongest forces. Okay, now here are two examples of molecules that have dispersion forces. Remember what we said, that anything with an electron cloud can have a dispersion force. So in other words, dispersion forces are present in all molecules. What you'll realize soon is that for these three types of intermolecular force that we're looking at, it's really important that you can look at your molecule, look at its symmetry and these kind of things, and how many atoms it's got in it and so forth, and decide what type of forces it's got and how strong they'll be. So if we look at these two molecules which have dispersion forces in, because all molecules have dispersion forces in, and we look at their boiling points, by the time you've done the organic topic, you should know that the formula of methane is CH4 and that the formula of ethane is C2H6. You might not know that yet, because you might not have done the organic topic yet, but anyway. What we can also see is that methane has a boiling point of around about a minus 160 degrees centigrade, whereas ethane's is about minus 90 degrees centigrade. So there's a big difference in their boiling points. Why should there be a big difference in their boiling points? Well, their boiling points will be influenced by their intermolecular forces, because how hard it is to separate one molecule from the next will depend on the force between those two molecules. Okay? this molecule is quite a lot smaller than this molecule. It has less atoms, it has, fewer atoms and fewer electrons than this one. And the fewer electrons you have, the smaller your electron cloud is, and the weaker your dispersion forces will be. Okay, so I suppose take-home points from this film are that all molecules will have dispersion forces that come about because of this mobile electron cloud randomly moving about the place, and the bigger the electron cloud is, the stronger the dispersion forces will be, and that will have an effect on your physical properties. Okay, so hopefully you know how to explain how dispersion forces arise and what causes their strength to vary. If there's anything here that we've mentioned that you're either confused about or want to simply comment on, then please feel free to post a comment on YouTube or to come and see me.